Inside every single one of our devices, your phone, your laptop, an electric car, there's a hidden component, a real unsung hero, working around the clock to keep things running safely. It's not the flashy anode or cathode materials you always hear about. Nope, this part is absolutely critical, but almost invisible. So today, we're going to pull back the curtain and talk about the battery separator.
All right, here's what we've got lined up. We'll start by introducing our unsung hero and its surprisingly high-stakes job. Then, we'll do a quick tour of the different types out there before we really zero in on the secret weapon inside our lithium-ion batteries. After that, we'll see how it stacks up against older battery types, and then take a look at what the future holds for this critical piece of tech.
So let's jump right in. To really get why this matters, we need to understand the sheer scale of the battery world and a fundamental problem that it's always had to solve.
Okay, so let's set the stage.
To appreciate just how important this little component is, you have to think about the scale we're dealing with. Even way back in the year 2000, the global battery market was already worth a massive $41 billion. I mean, today that number is way, way bigger, but a core engineering challenge at the heart of every single battery has stayed exactly the same.
And that challenge is this. How in the world do you pack two super reactive materials, your positive and negative electrodes, right up against each other, let them do their energy exchange thing, but, and this is the important part, prevent them from ever touching and causing a total catastrophic failure? Well, the solution is actually pretty elegant. It's the separator. I like to think of it as the bouncer at a really exclusive club. Its job sounds simple, but it's crucial. It has to keep two rowdy crowds, the positive and negative electrodes, physically separated, no touching, ever. But at the same time, it has to let the real VIPs, the charge-carrying ions, flow right through the velvet rope. Because without that flow of ions, the party's over. The battery's dead.
Okay, so what exactly is on the job description for this battery bouncer? Well, as it turns out, the list of requirements is, wow. It's so demanding, it sounds almost impossible to pull off.
This list really shows you the separator's contradictory nature. First, it has to be a perfect electrical insulator, block electrons completely. But at the exact same time, it has to offer almost zero resistance to ions, letting them just fly through like it isn't even there. It needs to be chemically stable, just sitting in a highly reactive electrochemical soup for years without degrading. It has to be mechanically strong enough to be stretched and wound on super-fast assembly lines, yet it also has to be incredibly thin. We're talking 20 microns. That's thinner than a human hair. Because any extra thickness is just dead weight that kills the battery's performance. Fulfilling all of these things at once is a genuine engineering masterpiece.
So with a job description that demanding, it's probably no surprise that engineers have come up with a few different ways to tackle the problem over the years.
Yeah, there are a few main approaches. The ones in our high-tech gadgets are usually these microporous films, and we're going to focus on those in a minute. For your everyday disposable batteries, you'll often find nonwovens, which are basically just mats of tangled-up fibers. Then things get a little more specialized. You've got ion exchange membranes, which are like super selective filters, only letting very specific ions get through. And then there's the cutting-edge stuff, materials like solid ion conductors, which are kind of the holy grail for safety because they're solid, non-flammable barriers that can still shuttle ions around.
But for now, let's zoom in on the real star of the show, the secret weapon that's inside pretty much all of the lithium-ion batteries that power our daily lives.
These separators are usually made from a type of plastic called polyolefins. Think polyethylene or polypropylene. There are two main ways to make them. The dry process is basically mechanical. You just stretch the plastic until these tiny slit-like pores open up. It's simpler, it's cheaper. The wet process is more of a chemical thing. You mix in a solvent and then remove it later, which leaves behind this beautiful network of uniform, interconnected pores. It costs more, for sure, but you generally end up with a tougher, more reliable separator, which is exactly what you need for high-performance stuff. And right here, you can see the specs for some actual commercial separators. Just look at how thin they are. We're talking 20 to 25 micrometers. But the most important detail, the real genius here, is that melt temperature. See how polyethylene, or PE, melts around 135 degrees Celsius, but polypropylene, PP, hangs on until about 165? That 30-degree difference, that's not an accident.
That is a brilliant and frankly life-saving design feature.
Which, of course, brings us to the most critical question of all. What happens when something goes wrong? When your battery starts to get dangerously hot? This is where the separator performs its most heroic act. See, in a lot of batteries, it's this clever 3-layer sandwich design. During normal operation, ions are flowing, everything's great. But if the battery starts to seriously overheat and hits 135 degrees, bam, that middle polyethylene layer melts. Its microscopic pores just collapse, and it turns into a solid wall of plastic. This instantly blocks the ion highway, shutting down the whole chemical reaction. But wait, if the middle is now molten goo, what keeps the electrodes from touching? That's the job of the outer polypropylene layers. With their higher melting point, they stay solid. They act like a physical scaffold, holding everything apart to prevent a catastrophic short circuit. It's just an ingenious built-in fuse.
And this brilliant 1-2 punch of material science, a low-temp shutdown to stop the reaction, followed by high-temp integrity to prevent a short, well, that's the battery's last and most important line of defense against thermal runaway.
Now, this whole sophisticated safety system is absolutely vital for high-energy lithium-ion batteries. But what about the older, water-based or aqueous batteries? How do things work in their world? Well, over there, the separator faces a totally different problem. In the non-aqueous world of lithium-ion, the big worry is chemical stability. But in an aqueous battery, like the good old lead-acid one in your car, the electrolyte is water-based, so the challenge is wettability. That polyolefin plastic is naturally hydrophobic. It hates water, like a raincoat. For the battery to work, that watery electrolyte has to soak into the separator's pores. So, manufacturers have to treat the material with special wetting agents, called surfactants. They basically act like a soap that helps the water get in and complete the circuit. And this table here really shows you how far that technology has come. Early materials like rubber and cellulose, they had pretty bad electrical resistance, which just wastes energy. Over time, we moved to PVC, and then finally to the modern polyethylene standard. This gave us great performance across the board, and it was envelopable, which is a fancy way of saying it was flexible enough to be wrapped around the electrodes by machines during manufacturing. A huge deal for cost and quality control. So, where does all this leave us? What's the path forward for these critical but often overlooked components? This quote, I think, just perfectly captures that unsung hero theme we've been talking about. It says that compared to the enormous amount of research poured into electrodes and electrolytes, very little work was being directed toward creating brand new separators.
The authors make a fantastic point. Historically, a lot of separators weren't even invented for batteries. They were just materials that were adapted from other industries. They were, good enough, but they weren't designed from the ground up for this specific, demanding job. And that creates a massive opportunity for innovation. Imagine designing separators that aren't just passive walls, but active components that can maybe signal the battery's health or enable entirely new next-generation chemistries.
And that really leaves us with this final thought. As we demand more and more from our technology, more range from our EVs, longer life from our phones, safer energy storage for the power grid, we are pushing our batteries to their absolute limits. The next huge breakthrough might not even come from a new electrode material. It might come from the humble, invisible separator. So the question is, who's going to step up? Who's going to innovate and develop the next generation of these invisible guardians? Their work might go unseen by most people, but it's going to be absolutely essential to powering our future.